made the connection between bijections and the cardinality of finite sets. In other words, for finite sets A and B, there exists a bijection F from A to B if and only if the cardinality of A is equal to the cardinality of B. In other words, if the sets have the same size. Now, is this going to be true for infinite sets? It turns out the answer is yes, and by definition. So this is how we're going to define the cardinalities of infinite sets. We're going to say that two infinite sets have the same cardinality if and only if there exists a bijection between them. If and only if there exists a bijection between them. And throughout the next few sections, we're going to show that some infinite sets are indeed larger than others using this cardinality sense, using this definition, while many other infinite sets that appear to be different sizes are in fact the same cardinality. And to do that, we're going to use a thought experiment referred to as Hilbert's Hotel, sometimes called the paradox of Hilbert's Grand Hotel. So we're going to consider a hotel that has just one long hallway. And in fact, it's infinitely long. So the rooms are numbered by the natural numbers. So the very first room is labeled 1. The second room is labeled 2. The third is labeled 3. And it just goes on forever. Now, Hilbert's Hotel is very popular. Generally speaking, there are no vacancies. Every room is full. And yet, they can often find ways to accommodate a new guest. So imagine that this hotel is full and that each of these sort of red labels here is just an indication that somebody's in that room. Now, a new guest arrives. No rooms are available. Every room has somebody in it already, but the manager has a simple idea to help make room for this guest. All the manager really has to do here is just ask that the guest that's in room 1 right now move into room 2. And then that the guest who's currently in room 2 move down to room 3. The guest in room 3 moves to room 4, and so on. So essentially, the guest that's currently in room N moves to room N plus 1. Everybody just moves one room down the hallway. The result is this, right? So now the guest who had been in room 1 is in room 2. The guest who had been in room 2 is in room 3, and so on. So we have infinitely many occupied rooms, but we also now have one room that's unoccupied, right? Nobody's in room 1 right now, which means our new guest has somewhere to go, right? The new guest is going to go into that first room, and right, we've found a way to occupy this new guest. Great. So it turns out that this would work if we had 2 new guests as well, right? So using the same idea, we would just ask for the guest who was originally in room 1 to move to room 3, the guest originally in room 2 to move to room 4, the guest originally in room 3 moves to room 5, and so on. So the guest who was originally in room N moves to room N plus 2. And the result is that we still have infinitely many occupied rooms, but now we have 2 new unoccupied rooms to accommodate those 2 new guests. Similarly, for any finite number of new guests, we can accommodate these new guests by just moving the existing guests down some number of doors. And so this suggests to us, for instance, that the cardinality of the set 1, 2, 3, 4, 5, the cardinality of the natural numbers, right? This cardinality is equal to the cardinality of the natural numbers plus 1 more, right? The natural numbers plus that new extra guest. So let's say the set 0, 1, 2, 3, and so on. And similarly, if we had 2 new guests, we could accommodate those as well. So this is equal to the cardinality of -1, 0, 1, 2, 3, and so on. We can fit them all into the same infinite hallway, so there should be kind of the same number of guests in the cardinality sense. Now, of course, we haven't really proved that super carefully. We'd want to use bijections for that, but we'll see an example of that in just a minute. Now, the question is, what if an infinite number of new guests arrive? So let's say we label these new guests G1, G2, G3, and so on. They're indexed by the natural numbers. Is it possible for us to make space for all of them? We can't use the same trick of just shifting everybody down, n many units, because you'd have to pick a specific n, right? You need to give good directions to the people who are already in the hotel. You can't tell them to move down infinitely many doors because they don't know what room to go to. But the manager can still find a way to accommodate these infinitely new guests using a slightly different trick. So what the manager requests is that the guest who was originally in room 1 is going to move to room 2. The guest originally in room 2 is going to move to room 4. The guest originally in room 3 is going to move to room 6, and so on. The result is that we end up with all of our old guests still accommodated, but only occupying the even-numbered rooms. So essentially, the rule that the manager is giving them is that the guest originally in room N moves to room 2N, right? 1 goes to 2, 2 goes to 4, 3 goes to 6, and so on. So they go to the room that's double the number of whatever their original room was. And now we have all infinitely many open rooms, right? So we would put G1 in the first room, the first unoccupied room, G2 in the second unoccupied room, G3 in the third, and so on. So we've been able to sort of create infinitely new rooms from the infinitely many occupied rooms. Now, essentially what we did is we moved the existing rooms into the even-numbered rooms, or the existing guests into the even-numbered rooms, and the new guests into the odd-numbered rooms. And so this kind of suggests to us that the set of natural numbers is equal to the set of integers. Well, okay, technically, right, we had this these are our original guests. And if we think about the new guests, G1, G2, G3, and so on, as our negative integers, what we've really shown is that the set of natural numbers is equal to the set of all of the integers except 0, right, I suppose. But we could still technically accommodate one more by just doing a combination of those two tricks, right? So first, shift all guests by 1, right? Then put 0 into room 1, which is now open, and then move each of these guests into room 2N based on where they currently are. Whatever room N you are currently in, move to room 2N, and now we still have space for guests, -1, -2, -3, and so on. Okay, so there is a way, to sort of show, or this at least suggest to us that the size of the natural numbers is equal to the size of the integers. What we really are doing here, and we're doing it sort of in a hand-wavy way, but we're constructing a bijection from one infinite set to another. So if we're considering the case where an infinite number of new guests have arrived, we can think about this as constructing a bijection from the integers into the natural numbers. So we think about the negative integers and 0 as our infinitely many new guests, and the natural numbers as the guests who were originally already in the hotel. By finding a way, or by finding a bijection from the integers into n, we're finding a way to accommodate all of the existing guests as well as all of the new ones into the original n many rooms, right, or natural number many rooms. So the bijection that we're using is going to be a piecewise one, which basically says f of n is equal to 2n if n is positive. In other words, if you're an existing guest in the hotel and you're already in room n, you're going to move to room 2n. And if n is less than or equal to 0, if you're one of the new guests, we're going to move you into room -2n plus 1. Right, we can see that the existing guests are going to end up in an even numbered room because 2n is going to represent an even number, and that the new guests are going to be in an odd numbered room, right? -2n plus 1 is going to be odd. Now, to show that this is actually a bijection, we have to do a number of things, right? We have to show that the function's well defined, first of all, that it's actually taking integers and mapping them onto a distinct integer or natural number. And we also need to show that it's 1 to 1 and onto. So let me just really quickly rewrite this function again here so we can refer to it. So 2n if n is positive, and negative 2n plus 1 if n is less than or equal to 0. So we need to show that this is a bijection in order to really justify that the cardinality of the integers is equal to the cardinality of the natural numbers. So to show that it's well defined, we want to make sure that for every integer input, you get a natural number output. Any integer has just one output, right? Because your input is either positive or negative, so you're either following the top rule or the bottom rule. There's only one output there. And the output is going to be a natural number because note that when n is positive, when n is a whole number that's positive, 2n is going to be a natural number. And when n is less than or equal to 0, and n is an integer, that would mean that negative 2n is going to be greater than or equal to 0, because you're taking a negative or 0 number and you're multiplying it by a negative. And so negative 2n plus 1 is going to be strictly greater than 0, and it will still be an integer, of course, because n is an integer. But this means that the output, negative 2n plus 1, is a natural number as well, right? We want to make sure this is well defined, that we're actually getting outputs in the desired set of the codomain, which is the natural numbers. So this is a well-defined function. We also need to show that it's 1 to 1. So to show that it's 1 to 1 just means if you feed two different inputs into this function, you get two different outputs. So let n and m be two distinct integers. To show that this function is 1 to 1, we must show that their outputs are not equal, right? F of n is not equal to f of m. We kind of have to address this in cases. If n and m have different signs, if one is positive and one is negative, then clearly these are going to be different outputs because one of them is going to be an even output and one of them is going to be an odd output. So f of n and f of m have different parity, have different even or oddness. So they're not equal to each other. And on the other hand, if you take two inputs that are both positive or you take two inputs that are both negative, then again, it's clear that f of n and f of m are not equal to each other because we'll either have 2n is not equal to 2m when n is not equal to m, and negative 2n plus 1 is not equal to negative 2m plus 1 when n and m are not equal to each other. That means that those outputs, f of n and f of m, are not equal to each other. Okay, so we know that this is a one-to-one function as well, an injective function. The last thing that we need to show is that the function is onto, or surjective. That means that the codomain is equal to the range. Remember, the codomain was set to be the natural numbers, so what we're trying to show is that every natural number actually shows up as an output to this function. That is to say, if we're thinking about this as Hilbert's hotel, every room ends up with somebody in it. So this, again, is not too hard to show, although we have to do it in cases again. So let y be any number in the codomain, let y be any natural number. We must show that there is an integer n, so there exists an n in this set of integers, such that f of n is equal to y. Show that there's something that's going to map onto y. Now, if y is even, then that means that y is equal to 2n for some natural number n, also for some integer n, but in this case, remember, y is a natural number, so 2n, n will be a natural number as well. And so we have that that's the n that we're looking for, because f of n is going to give you 2n, which is going to give you y. So yes, that y is going to show up as an output of this function. On the other hand, if y is odd, we have that y is equal to negative 2n plus 1. And so this one's a little bit trickier. We have to try to figure out what n's going to map to it. But essentially what we're doing is we're solving this equation for n to get us that the number, setting n equal to the opposite of y minus 1 over 2. We're going to claim that this is either a negative integer or 0, as y is odd. So when we subtract 1 from y, we get an even number. Even number divided by 2 is going to be a whole number. And it will, well, I guess, okay, since y is odd, y minus 1 over 2 is going to be a positive integer because y is positive. Therefore, the opposite of y minus 1 over 2 would be a negative integer, which would mean that f of n is equal to negative 2n plus 1, or negative 2 times the opposite of y minus 1 over 2 plus 1, which is canceling the negative 2, we get y minus 1 plus 1, or y. So we get y as an output as well. All right, so the range is equal to the codomain, which means that the function is onto. Okay, so now that the function is one-to-one and onto and well-defined, that means that it's a bijection. F is a bijection from the integers to the natural numbers, which means by our definition of the cardinality of infinite sets, the cardinality of the integers is equal to the cardinality of the natural numbers, which is great, right? And maybe a little bit surprising because the natural numbers is a proper subset of the integers. But the way that we're defining cardinality, we think about them as being the same size. So a natural follow-up would be to determine whether all infinite sets have the same cardinality. For instance, can we find a bijection from the natural numbers to the rationals? Can we find a bijection from the natural numbers into the reals? These are things that we're going to explore in the exercises as well as in the next section.